Hi, I'm Brian Freer, tutoring high school physics. Today's topic, electric potential energy and electric potential. Whenever you have a charged particle inside an electric field, that charged particle is going to have some potential energy due to the electricity. When that charged particle moves within that electric field, the potential energy that it has will change. We can calculate that change using this equation. Delta U sub E, or the change in electric potential energy, is equivalent to negative KQQ over R. So each of those Q's is going to be a different charge. One is going to be the moving charge, the other is going to be the one generating the electric field. And R is going to be the distance moved by the moving charge. So let's take this for example. We have two charges, one positive, one negative, and the positive charge at 2 coulombs moves 3 times 10 to the third meters close to the negative charge at 2.5 coulombs. So what is the change in potential energy for our positively charged particle? Well, let's calculate it. So delta U sub E equals negative coulombs constant 9 times 10 to the 9th newtons times meters squared per coulomb squared times 2 coulombs times negative 2.5 coulombs. Now I'm saying negative because it is a negatively charged particle. Carry that into the coulomb charge. So finally, over a distance of 3 times 10 to the third meters. So let's first get rid of this denominator. Well, everything's negative first. 9 divided by 3 is 3, and 10 to the 9th divided by 10 to the third is 10 to the 6th. That's Newton meters per coulomb squared. And 2 coulombs times negative 2.5 coulombs gives us negative 5 coulombs squared. We finish off the multiplication. 3 times 5 is 15, but let's keep it in scientific notation. So 1.5 times 10 to the 7th, as opposed to 10 to the 6th, Newton meters, or joules. You'll notice that I've written up here as well that the change in electric potential energy is equivalent to the negative work done. So if we want to find the work, that would just be negative our answer, negative 1.5 times 10 to the 7th joules. And the negative work makes a lot of sense because that indicates an event that occurs spontaneously. And a positive charge is spontaneously attracted to a negative charge, so we would expect that when a positive charge moves closer, that it would be a spontaneous event with negative work. Alright, next up, electric potential. This is very similar to the electric field, but recall that when we measure the strength of an electric field at one point, we're finding the force that's going to be exerted on a charged particle for every coulomb of charge. This, the electric potential, instead measures the electric potential energy that that charge is going to have per coulomb of charge. And so the equation is V, our electric potential, equals KQ over R. So for some charged particle exerting that electric field, we would take the Q, put that in, we've got our K, and then R is the distance from that particle. So let's say that this is where we are. We're 3 times 10 to the third meters from our charged particle with 2 coulombs. Let's calculate our electric potential. Well, first off, as always, we have coulombs constant, 9 times 10 to the 9th, newtons times meters squared per coulomb squared, times our charge of 2 coulombs over a distance of 3 times 10 to the third meters. So you've seen me cancel these things out several times. Now 9 divided by 3 is going to be 3, and then this is going to be 10 to the 6th. And let's see, Newton meters per coulomb squared times 2 coulombs, so we get 6 times 10 to the 6th Newton meters per coulomb. This is actually a very special unit that you're probably familiar with. That's 6 times 10 to the 6 volts. And so that's our electric potential. To recap, every charge in an electric field has electric potential energy. When it moves, we can calculate the change in its electric potential energy through the equation negative KQQ over R, where K is coulombs constant. Each of those two Q's is one of the charges, either the moving one or the one generating the field, and R is the distance moved by the moving charge. The change in electric potential energy is also equivalent to the negative work that is performed. Electric potential is a measure of the electric potential energy that a charge will have at a certain point at a certain distance away from the center of an electric field. And we calculate that with the equation V equals KQ over R, where Q is the charge generating the electric field and R is our distance away from it. The units that we'll receive from this equation is Newton meters per coulomb, or the more commonly known volt. Alright, that's all for now. Again, I'm Brian Freer. See you next time.